This slide depicts the rate of heat transfer across a barrier. We've got here a barrier with thickness x, and across which there is a temperature gradient. So on the one side, the hot side, we have a temperature Th for T hot, and on the cold side here, we have a temperature Tc, T cold. So that we have a temperature difference delta T across the barrier given by the difference between Th and Tc. So delta T is Th minus Tc. Now the rate of heat flow across that barrier will be determined by this temperature difference, delta T. It will also be determined by the thickness of the barrier, and one imagines it must also be determined by the material from which the barrier is made. So we want some property of that barrier which will influence the rate of heat transfer. And that property we call K. It's the thermal conductivity of the barrier. The rate of heat transfer per square meter of barrier is given by this expression, Q. The rate of heat transfer in watts per square meter is K delta T over X. Now if you think about it, that makes some kind of sense. What it says is that the thicker the barrier, the less the heat flow, all else being equal. The greater the the greater the temperature difference from one side to the other, the greater the rate of heat transfer. So the bigger that difference, the more rapidly heat will flow from the hot to the cold. It also says that the rate of heat transfer has to do with the material of which the wall is built. And the property that we choose, the thermal conductivity, is on the top of this expression. So the thermal conductivity is a property where the bigger it is, the more rapidly heat will flow across a barrier of given thickness with a given temperature difference across it. In fact, the thermal conductivity is such that you would expect it to have a high value for good conductors of heat, as the name would suggest, and a low value for poor conductors of heat, what we call insulators. In fact, the best insulators, the best insulators that are used in the built environment, these are the things like the PUR and PIR, kind of proprietary foil-backed stiff foam boards that you see on building sites everywhere, made by companies like Kingspan, Celotex, Knauf and the like. They have thermal conductivities nudging towards 0.02 watts per Kelvin meter. So get that? The unit of the thermal conductivity of a material is watts per Kelvin meter. And it's a material property, not a property of a particular barrier. It doesn't matter how big the thing is, or how thick it is, or wide it is, or whatever. It's a material property, and it's something you can look up. So the units are watts per Kelvin meter, and are low value as possessed by the best synthetic types of insulation used in the built environment are about 0.02 watts per Kelvin meter. Now, typically, the best performing natural insulators have thermal conductivities about twice that. And what that means is that if you want to get the same rate of heat transfer across a wall with natural insulation for a given temperature difference across that wall, then you're going to need twice the thickness of wall. Compared to a wall where the insulation is this PUR, PIR synthetic stuff with a thermal conductivity of 0.02. So the higher the thermal conductivity of a material,